Welcome, welcome, welcome to the glamorous world of drilled shafts. Yes, you heard that right. While everyone else is watching cat videos, we're about to dive deep, literally, into holes in the ground. This is the Drilled Shaft Field Manual, Construction, Inspection, and Integrity Verification. Think of it as Netflix for geotechnical engineers, but with way more concrete and significantly fewer plot twists. Brought to you by the FHWA, because nothing says exciting Friday night quite like deep foundation inspection protocols. Buckle up, Buttercup. We're going underground. Let's take a trip down memory lane to the 1890s. The era of handlebar mustaches, top hats, and the Chicago method. Picture this. Workers hand-digging massive holes with timber lagging, thinking they invented caissons. Spoiler alert, they didn't. It's like calling a sandwich a deconstructed loaf experience. But hey, give them credit. No power tools, just pure grit and questionable workplace safety standards. Fast forward to today's modern drilled shaft. Large diameter, single column support, transferring loads through friction and end bearing like a boss. We've gone from hope and timber to science and steel. Evolution, baby. All right, so you've dug a giant hole. Congratulations! But here's the problem. Holes have this annoying habit of collapsing. Rude, right? So we've got 3 methods to keep Mother Nature from ruining our party. First up, the dry method. Only for stable ground with minimal water. It's the "I hope this works" approach. Water inflow must be less than 12 inches per hour, or you're basically building an impromptu swimming pool. Next, the casing method. When the ground is about to cave faster than your New Year's resolutions. We literally seal out the groundwater with steel casing. It's like putting the earth in a turtleneck. And finally, the wet method, also known as the slurry method. We use hydrostatic balance, where slurry replaces casing. It's mud-tastic. Think of it as making the world's most boring smoothie, then using it to hold back thousands of tons of soil. Science! Meet the star of our show, the drilling rig. With its Kelly bar and rotary table, it's basically the transformer of construction equipment. And just like any good craftsman, our rig needs the right tools. Let me introduce you to the squad. Flight auger, the overachiever. General soil excavation? No problem. It spirals through dirt like a giant corkscrew through the world's least appetizing wine cork. Drilling bucket, the cleanup crew. Removes loose material and slurry. It's the janitor of the drilling world, and we respect that. Core barrel, the rock whisperer. When you hit rock, this bad boy cuts through like a boss, creating that perfect rock socket annulus. Cleaning bucket, the perfectionist. Final base cleanout before concrete goes in. Because nobody wants a dirty bottom of their shaft. We're talking about construction here, people. Together, they're like the Avengers, but for making holes. Slightly less dramatic, infinitely more practical. Ladies and gentlemen, feast your eyes on the Cage. No, not Nicolas Cage, though honestly he'd probably be more entertaining. This is a rebar cage, the skeleton that gives our concrete shaft its backbone, literally. Let's break down this steel anatomy. Longitudinal bars handle vertical loads, They're the weightlifters of the operation. Transverse ties provide confinement. Think of them as the supportive friend who keeps everyone together during tough times. Spacers and feet center the cage and maintain concrete flow. They're the diplomats, making sure everyone has their personal space. And those CSL access tubes? They're for integrity testing later, because trust issues are real, even in construction. Safety critical alert! See those Crosby clips? They're required for lifting bar splices. Forget them, and things get droopy. And in the world of structural engineering, droopy is not the vibe we're going for. Field note: ensure minimum concrete cover and verify splice length per design. Translation: measure twice, pour once. Avoid a career-ending oops. And now, the moment we've all been waiting for. The pour. This is where things get real, folks. We're using the Tremy method, which is French for please don't mess this up. Here's the deal. We need minimum 5 to 10 feet of Tremy pipe embedment. The concrete displaces the slurry from the bottom up. It's like a very slow, very expensive lava lamp. And here's the golden rule. Tattoo this on your forehead. Keep the tip buried. I repeat, keep the tip buried. Why? Because if that Tremy pipe tip breaks the surface of the concrete, if it breaches, you get defects. And defects mean someone's getting a very awkward phone call about why $1 million foundation has more holes than Swiss cheese. The concrete should displace upwards smoothly, pushing out the slurry like the world's slowest toothpaste tube. Elegant? Maybe not. Essential? Absolutely. Time to put on your detective hat, because we're about to read a concrete volume plot like it's the New York Times bestseller list. This graph tells us everything about what's happening underground. It's like an X-ray for your shaft, but without the radiation concerns. See that dashed line? That's the theoretical volume, what should happen if the universe played fair. Spoiler, the universe does not play fair. Shaft 1 shows a bulge. That's when the hole expands because we hit a soft soil stratum. The Earth is basically saying, I'm uncomfortable with this. Let me spread out. Then we've got a cavity, a sudden volume spike, meaning there's a void. Someone screamed, "Surprise!" underground, and not in a fun way. Shaft 2 shows a neck, a restriction or collapse where we're using less concrete than expected. The hole got shy and squeezed itself. This is not what we want. The goal? Stay close to that theoretical line. Deviate too much, and you're starring in an episode of Construction Nightmares. Nobody wants that show. All right, we're getting down and dirty. Literally. Bottom cleanliness might sound like a weird spa treatment, but it's actually the foundation of the foundation. Mind blown. First, we have the thump test, which is exactly what it sounds like. Drop a weighted tape down there and listen for the thump. Firm base? Good. Soft, squishy sediment? Bad. It's like knocking on a door to see if anyone's home, except the door is 80 feet underground and made of mud. Then we level up with the shaft inspection device, or SID. It's basically a robotic inspector that goes down there with cameras to give us visual confirmation. The criteria? Less than ½ an inch of sediment depth. Because we're not building sandcastles here, people. We're building foundations that need to support actual buildings with actual people inside them. Think of it this way. Would you build your house on a pile of oatmeal? No? Then don't pour concrete onto loose sediment. Your future self and the structural engineer will thank you. Pop quiz. What's the most thrilling part of construction? Did you say paperwork? Correct. Welcome to everyone's favorite topic, documentation. Cue confetti that no one throws. This is the drilled shaft soil excavation log, and it's about to become your new best friend. Here's the pro tip that'll save your bacon. Use elevation, not depth. Why? Because elevation is fixed. It doesn't care about where you started digging or how confused you were that morning. Depth is relative, and relatives can be unreliable. Track open time and pour breaks, because time matters when you've got an exposed hole fighting gravity and groundwater. It's like tracking how long milk has been out of the fridge, except with higher stakes and more concrete. Correlate with borings, meaning double-check that what you're digging through matches what the geotechnical report promised. If they said clay and you're hitting granite, someone's having a bad day. And don't forget your inspector's kit: stopwatch, measuring tape, field book, and calculator. You're basically Batman, but instead of a utility belt, you've got nerdy measuring tools. Still cool. Trust me. Welcome to the world of integrity testing, where we use science fiction technology to make sure your concrete shaft isn't secretly a disappointment. Because trust is great, but verification is better. First up, CSL, Cross-Hole Sonic Logging. The industry standard. We send ultrasonic pulses between tubes embedded in your shaft. It's like giving your foundation an ultrasound, minus the grainy baby pictures. If the waves move correctly, you're golden. If not, well, time to have that awkward conversation. Next, tip, thermal integrity profiling. This one measures hydration energy. Concrete generates heat as it cures. Who knew it was so passionate? Heat sensors on the rebar cage track temperature changes. It also tests cage alignment, because even cages have posture issues. Then there's LST, low strain testing, the pulse echo method. Whack the concrete with a hammer and listen to the echo. It's like echolocation, but you're the world's least interesting dolphin. Best part? No tubes required. Finally, gamma-gamma testing, the nuclear option. Literally. We lower a nuclear density probe down a tube for localized checks. It's fancy, it's expensive, and it sounds like something from a Bond movie, which automatically makes it cool.